All right, welcome. Today, we're going to take a super fast journey through the history of data. We're going to see how we went from just, organizing information in these neat digital filing cabinets to building the massive, complex architectures that are basically the brains behind artificial intelligence. Okay, let's just dive right in. You hear this phrase all the time, right? Data is the new oil. But let's be real, oil is pretty useless without a refinery. Well, that's where data architecture comes in. It's the refinery, that essential, often invisible infrastructure that organizes, processes, and actually makes data useful for, well, everything from your bank account to your Google search. So let's start at the beginning. Our story really kicks off in a time when the biggest challenge was just keeping things tidy. This was the age of order, where the whole goal was to bring some much-needed structure and reliability to business records. Now, right from the start, we see this great split in the data world. You see, data has two very, very different jobs. On one side, you've got OLTP, which is all about running the business day to day. Think of a super fast ATM withdrawal. On the other side, you have OLAP, which is for analyzing the business, like running a huge, complex yearly sales report. And trust me, trying to do both on the same system is just a recipe for disaster. It's kind of like trying to race a car while the pit crew is trying to change the tires. It just doesn't work. The hero of this first age was, without a doubt, the relational database, or RDBMS. The best way to think of it is as the ultimate digital filing cabinet. It brought strict rules, it brought organization, storing everything in these neat, predictable tables with rows and columns. I mean, for decades, this was the absolute foundation of trustworthy data. So what made these things so trustworthy? Well, it all comes down to these four principles, famously known as ACID. Atomicity means a transaction is all or nothing. Your money transfer either fully completes or it doesn't happen at all. Consistency makes sure the data always follows the rules. Isolation keeps one transaction from messing with another. And durability means that once something is saved, it's permanent, even if the power goes out. For things like banking, these rules aren't just nice to have, they are absolutely non-negotiable. And then, the internet happened. Suddenly, this calm age of order was just overwhelmed by a complete tsunami of new, messy, unpredictable data. And the old systems? They really started to crack under the pressure. This new challenge was defined by what people call the V's of big data. First, there was the sheer volume of it. Then the relentless velocity, the speed it was coming at you. And of course, the incredible variety. It was no longer just neat tables, but text, images, video, you name it. There's even a fourth V, veracity, which is all about how can you even trust any of this messy stuff? Yeah, the rigid, old-school relational database, it just wasn't built for this kind of chaos. And this slide really gets to the heart of the problem. See, traditional databases scaled up, or vertically. That means you had to buy one single, giant, super powerful server. It was incredibly expensive, and you'd eventually hit a hard limit. The new world demanded horizontal scaling, or scaling out. You just add more cheap, regular servers to a network. It was way cheaper, way more flexible, and it could handle pretty much anything the internet could throw at it. So the solution that popped up to handle all this was the NoSQL database. The name literally means not only SQL, and it was a whole new philosophy. These systems were built from the ground up for the kind of flexibility and massive scale you need for the web. And they made a really crucial trade-off. They sacrificed some of that strict ACID consistency in exchange for always being available and super fast. So what does sacrificing consistency actually mean in the real world? Well, it means you embrace something called eventual consistency. Think about it. When you post a photo on social media, your friend across the world might see it a few seconds later than your friend next door. That little delay, it's totally fine for a social network. But for a bank transfer, oh, that would be a complete disaster. That right there is the trade-off. Okay, so we figured out how to handle all this live, messy data. But that led to the next big question. How do we pull all this incredibly diverse data from all over the company into one single place so we can actually analyze it? Two main ideas emerged. On one side, you have the data warehouse. Think of this like a pristine, perfectly organized library. You carefully design the shelves, that's the schema, first, and only then do you load in your clean, structured books. On the other side, you have the data lake. This is more like a giant, messy garage where you just dump everything. Raw, structured, unstructured, you name it. And you figure out how to organize it later when you actually need to find something. The warehouse was super reliable, but it was also expensive and really rigid. The lake was cheap and flexible, but it could easily turn into a messy data swamp. So naturally, the industry evolved again and created the data lakehouse. And the goal here is pretty simple. Get the best of both worlds, the low-cost flexibility of a lake combined with the reliability and quality of a warehouse. And that brings us right up to today, to the age of AI. The challenge now is no longer just about storing and counting data. No, it's about teaching our machines to understand what that data actually means. And here's the fundamental difference. A traditional database is awesome at finding exact keyword matches. But if you want an AI to understand that the king of the jungle is related to a lion and not a member of royalty, you need a completely different way of thinking. So how do you search for concepts, not just characters on a screen? The answer is the vector database, and this thing is a total game changer. It takes concepts, words, sentences, even entire images, and it turns them into these long lists of numbers called embeddings. In this weird mathematical space, concepts that have similar meanings end up with vectors that are really close together. So king is close to queen, but it's really, really far from banana. The database isn't looking for exact matches, it's finding the nearest conceptual neighbors. It's pretty wild. Now, why is this so incredibly important? Because large language models have this massive problem. They can hallucinate. That means they can confidently and very convincingly just make up facts that are completely false. For any serious business, that's an absolute deal breaker. This is how we fix it. The technique is called retrieval augmented generation, or RAG for short. When you ask a question, the system doesn't just go straight to the AI. First, it zips over to a vector database to find relevant factual documents. Then, it augments, or adds, the facts it found to your original question. And finally, it tells the AI, okay, generate an answer, but you can only use these facts I've just given you. It literally grounds the AI in reality. Okay, for our final chapter, let's look at a really special kind of data. Data that is always in motion, where its value can just disappear in an instant. This brings us to our final big architectural split, batch versus stream processing. Most of what we've talked about so far is actually batch processing. You collect big chunks of data and process them every so often, like for a nightly sales report. Stream processing is completely different. It handles data event by event, in real time, as it's happening. This is what you absolutely need for things like credit card fraud detection, where you need an answer right now. And the undisputed king of this streaming world is a technology called Apache Kafka. Honestly, the best way to think about it is as the central nervous system for a company's real-time data. It just manages these continuous flows of information, letting all these different systems react to events the very moment they happen without ever having to talk directly to each other. So there you have it. In just a few minutes, we've gone from rigid, orderly tables to flexible data lakes to AI databases that actually understand meaning, and finally, to these real-time streams of consciousness. It has been an absolutely incredible evolution, which really just leaves us with one final thought. What's next? What's going to be the next huge challenge that forces us to completely rethink how we manage data all over again?